This worked example contains a publicly available set of PPAR gamma PIC50 data, which contains a number of chemical series. Matched series analysis is used to identify when a substitution from one series has a high likelihood of improving the binding of another series at PPAR gamma. This approach is then further applied to help analyse the project's SAR to generate hypotheses regarding binding modes and identify possible anomalous measurements for further investigation. A matched series is a series of compounds that are identical except for different substituents at a single point. In this worked example, suggestions are derived from comparing matched series within the input data, highlighting where SAR does or does not track between chemotypes. The suggestions are based on the premise that a matched series with similar activity order in more than one chemotype means that those groups occupy a similar binding environment. Given a similar binding environment, groups that have been shown to be better binders within one chemotype have a strong likelihood of being better binders to the target in another. Conversely, the situation where the matched series SAR of one chemotype differs from another also provides useful information, because this may indicate that a change in binding mode has occurred or that an assumed overlay of the chemotypes is not valid. First, we open the project's file PPAR project by using the File Open menu. You'll see a spreadsheet containing 666 structures and the measured PIC50 values for PPAR gamma, along with two calculated columns for log P and log S at pH 7.4. You'll also see that there are three visualizations that have been saved in the project file. The histogram shows that there is a wide spread of activities across 5 orders of magnitude in this set. The scatter plot in the visualization tab shows that the most active compounds tend to have higher log P values, which may not be desirable. The chemical space plot, in which the points are again coloured from red for low PIC50 values to yellow for high PIC50 values, shows the diversity of the set. With good activity spread across the different chemical series, finding the consistent or inconsistent SAR across this set would be a laborious process. To start the matched series analysis, change to the Nova tab and then click the arrow button at the bottom. Select the Matched Series Suggestions option and click Next. In the dialog box that appears, you can specify which property column you wish to improve. The PIC50 nanomolar column is the default option, and we want to find suggestions that increase this value. In this exercise, we only want to search within the input dataset, so untick the box next to Chemical Knowledge Base and tick the box above it to use matched series identified in PPAR gamma IC50 data instead. Click the Next button to continue. At this point, you can change the parameters for the suggestions returned. In MATSI, the support for a suggestion comes from the number of times it has been observed. The more frequently the input series occurs in the same order, the more likely it is that the suggestion will be an improvement. In a small dataset, however, the frequency of occurrences is likely to be low, and so in this example we will concentrate on the SAR transfer method. With SAR transfer, the support for a suggestion comes from a long series of derivatives that show a consistent trend within several chemotypes. The default minimum number of derivatives, 8, is too large for this set, so we will reduce this to 3. In this example, we also want to see if there are cases where the SAR of the different chemotypes does not match, so we will also reduce the minimum series correlation for which results will be reported. Untick the box next to Calculate MATSI Suggestions. In the Calculate SAR Transfer Suggestions section, change the minimum length of matched series to 3 and reduce the minimum series correlation to 0.1. Click the Next button to continue. Here you can give the output dataset of suggestions a different name and control the data that are reported in the output. Tick the Show in Card View option and click Next. In the last step, you can choose structural filters to exclude certain chemical groups. In this case, we will use the defaults, so click Finish to begin the matched series analysis. The suggestions are returned in Card View as a series of networks. Each new suggestion in the network is coloured by the matched series that inspired it. These matched series from the input dataset are the white cards in the networks. To assess how well these series correlate, and hence how well the SAR transfers between the chemotypes, we will colour the cards by the max correlation property. Click on the Colour button at the top of Card View. In the Colour by dialog that appears, select the Cards tab and change the Colour by drop-down to select the max correlation column. Then click OK. Now we can see where the red and yellow cards indicate poor and good SAR transfer respectively. To help us explore the underlying data in more detail, when the card representing a suggested compound is selected, the matched series of compounds giving rise to the suggestion is highlighted by the blue links between the cards. The display in the Nova tab also changes to show the correlations in SAR that prompted the matched series suggestion. Click on the Find button on the right-hand toolbar to bring up the Find dialog. Now type in SAR 6-8 to search for a series containing this name, and then click Find Next. This will highlight one of the series within this network and display the compound in the suggestion area of the Nova tab. If you try this for yourself, note that the suggestions at the bottom of the network may be ordered differently. Where there is a high correlation between two matched series, we can have confidence that the SAR may be transferred. Here we can see that the ether substituent in the benzothiophene series increases the activity as the size increases, with the cyclopropyl methyl group being the most active in the series of 6. Note that a pop-up showing the scaffold for each series can be seen by hovering the mouse over structures. As one might have expected, the naphthyl series shows the same SAR for the first 5 derivatives, and so the suggestion given is to make the cyclopropyl methyl derivative in the naphthyl series, because it is expected to be more active. We will now consider another series, which we can find again using the Find tool, this time searching for SAR 4-26. The cards are coloured by the correlation of the SAR in the suggestion series to the SAR in the rest of the dataset. This group contains different suggestions for substituted phenols adjacent to a beta-lactam group. The SAR for the supporting series is consistent for an overlay of those series where the hydrophobic groups are binding in the same pocket, then leading, via a flexible linker, to the acidic group at the other end of the molecules. Interestingly, the suggestion for derivatization is adjacent to the acidic group in the beta-lactam series, i.e. at the other end of the molecule. This SAR transfer indicates 3 possibilities. There's an overlay of the series where the paraquinone ether is bent back towards the acid, assuming the linker is sufficiently flexible. There is another similar aryl binding pocket not yet explored in the thiazolene dione or the benzopyran series. Or the SAR transfer is simply a coincidence. We typically look for matched series with a high correlation to give confidence that the suggestion will have an improved activity. Therefore, suggestions for matched series with a poor correlation are not likely to be relevant. Examples of these are shown by the orange-coloured cards in this network, and as we can see here, they are derived from a diaryl sulfonamide series where one might not expect the rings to be binding in the same area, as this series does not have an obvious acidic group. However, looking for series with low correlation can highlight discontinuous SAR that might be derived from rogue assay values. The final series we will examine we can find as before, this time searching for the text SAR 4-28. The network shows that the SAR in the hydrophobic tail region of the benzopyran series matches that of the glycine derivative series, the top row of yellow cards, when the series is only 3 derivatives. However, when the 4th derivative is included in the match series, the SAR suddenly does not match derivatives in the thiazolene dione series, the second row containing red cards. From the inspection of one of these thiazolene dione series, we can see that the central anisole derivative has lower activity than one would expect. The differences between compounds in this SAR series as a whole are very small and within the error of the assay, so lower correlations will occur just by chance. But the reduction in activity of the methoxy derivative significantly reduces the correlation and appears anomalous. This is emphasized by examination of the longer series of 5 compounds where the suggestion cards are all colored orange. These compounds come from a very similar thiazolene dione series where the thiazolene dione is para to the linker rather than meta. And again, there is a good correlation with the benzopyran series. This would suggest that it would be useful to retest the activity of the methoxy derivative of the meta-thiazolene dione series to confirm this result. This worked example has shown that the analysis of the correlating and non-correlating SAR series enables hypotheses regarding compound alignments or their binding modes to be formulated and highlights anomalous data points in a way that is complementary to simple matched molecular pairs analysis. The matched series analysis tool within Nova also provides suggestions for further derivatives that are likely to improve a desired endpoint and can help support or disprove these binding hypotheses. The applicability and suitability of suggestions also relies on many other compound properties, so the output dataset can be further prioritized in StarDrop, for example using predictive models of physicochemical ADME or target activity properties and using probabilistic scoring for multi-parameter optimization. Examples of the use of these methods can be found in some of the other worked examples, which you can find in the tutorial section of the Optibrium community.